semester, somewhere in the middle of the December. As of today, so we will start with Alexey Nikitin. So briefly, Alexey studied astronomy in National University of Kharkov in Ukraine. He defended his PhD thesis from Institute of Low Temperature Physics and Engineering and Institute for Radio Physics and Electronics in the same city. Then he moved to Zaragoza to work on the photonics between 2007 and 2013. Later on, 2013, he moved here to San Sebastian as a Ikerbasque research fellow to join nanoGUNE. And later on, 5 years later, was promoted as a Ikerbasque research associate to join DIPC, where he basically developed his own research. So I have to mention, let's say, interesting list of awards. So first of all, he was awarded twice by Samsung Electronic Company in 2002 and 2004. He also obtained a Ukrainian President Grant, which is the most prestigious Ukrainian fellowship for young scientists in 2004. Then also individual grant INTAS from European Union to move to Spain. Then Juan de la Sierva Fellow, Ikerbasque, as I said before. And last year also he got Beca Leonardo by BBVA. So in terms of the research, so I think he is pretty known in this community for his very strong contribution to the low dimensional materials. And this is where we're gonna have the, let's say, opportunity to hear about this work. So please, the floor is yours.
Okay, thank you very much, Marek. I hope you could hear me from here. Also hope I will not fall down. So I'm really proud to be a part of the DIPC community. It's my pleasure. Also, thank you all for coming, although I see people not only from DIPC. So I will talk today about an activity that we have been doing in the group for several years, which is hyperbolic light. So the talk consists of basically two words, hyperbolic and light, and I have to address both of them. So I will explain you what I mean with hyperbolic and what I mean with light. This is my challenge for today. I also would like to highlight that I'm a part of another community, which is Photonics, which was boosted by Javier Aispura. So there are many, many groups here in San Sebastian. I just mentioned a few of them, mainly the people to whom I have collaborated or have some links. But these are mainly the group leaders. And so you have to multiply the number of these people by 5 or by 10 to realize how many people are doing optics in San Sebastian. And this is our group, two-dimensional nanophotonics group. So by talking today, I represent all of these people, which are PhD students. And I'm really happy to work with them because these people are very independent, so they nearly do not need supervision. I just observe externally, give some advices. And to prove what I say, you could see that within the last 3 years, all of them have got their covers in different journals. I think except of Kirill, Kirill, I think we will make another one for him, but he has so many papers, maybe he doesn't need cover. This is the outline of my presentation. This is what I will be talking about today. At least I will try to talk about all this stuff. So I will introduce you in the field of hyperbolic nano-optics, basically with natural crystals, van der Waals crystals. Then I will show you how we found an interesting platform of experimental studying of hyperbolic nano-optics. Then I will show you two interesting findings, refraction and focusing of hyperbolic waves. Then we will see, so it's called twisted nano-optics, how light propagates in twisted slabs of polar materials. And then if we have time, we will see some results on coupling between molecules and light. I'm not sure I will reach to the last part because I prefer to make it easygoing. So maybe I dedicate more time to some basic things so that you feel comfortable. But if I fail in explaining you something, this would be my fault. You could punish me with questions then later. So let's start with the introduction with the hyperbolic nano-optics. In general, we get used to light, perceive light with eyes, which propagates through free space. So like we see light emitting from light-emitting diodes, for example. And this is light traveling in free space, which transmit energy or information. But it has a very strong limitation, which is called diffraction limit. So what does it mean? It means that since light is an electromagnetic wave, you cannot you cannot confine this wave in a volume which is smaller than the half of the wavelength. So this, as a consequence, you cannot observe objects which are smaller than the wavelength of light, and you cannot transmit information or energy in the form of light through waveguides with a diameter, for example, like this would be optical fibers with a diameter of a fiber which is much smaller than the wavelength. So you cannot manipulate light on very small dimensions. And this is our challenge. This is a challenge of the whole nano-optics, to try to manipulate light on very small scale, namely on nanoscale. And interestingly, there is a type of electromagnetic waves which is called evanescent waves, which are waves whose amplitude decays exponentially in one of the directions. And the diffraction limit is not strictly applied to these kind of waves, which is good, which means that we can overcome it. So using evanescent waves is a way to make nano-optics. An example of such evanescent waves could be found in a university lab. For example, you take a prism, normal prism made of glass, and you shine with a laser beam. And then there is a critical angle at which the light cannot be transmitted through the prism. You just observe the reflected beam, so the energy cannot be transmitted to the opposite side of the prism face. But if you approach your eye directly to the surface or very close to the surface, then you could observe this light. Because as I said, the evanescent field just decays exponentially, but it is there. And this is the most simple example, I would say, of evanescent wave. But for us, another kind of waves is more relevant, and namely, these waves are called surface waves. Surface waves in nature we could observe daily. For example, you observe surface waves. These are capillary waves on water. When a drop falls on the water surface, you could observe these waves emanating from the point where drop touches the surface of water. The circular waves decay. And the amplitude of those waves decays exponentially into the surface of water, so they are evanescent waves. And in optics, there is a very important analogy of such waves, which are called surface Plasmon polaritons. Because, for example, in metals, we have many free electrons which could travel. And if you, instead of droplet, you place a nanoparticle and then you shine it with light, then this nanoparticle could induce charge oscillations in the metal, oscillations of electrons, which induces charges. And these charges are coupled to electromagnetic fields. And this sophisticated object is called Plasmon polariton. And this is what we mean with light. When we talk about light, we talk about polariton. Namely, we talk about electromagnetic fields coupled to some excitations in matter. And in case of matter, it's very important to also note, if we represent the dielectric function as a function of frequency, the dielectric permittivity, which is simply the proportionality between the field outside of the media and inside, then at certain frequency, it takes zero value, which is called, at this condition, we have the so-called volume plasma. But at lower frequencies, we have the region where epsilon is negative, and this is the range, spectral range, where we could have surface Plasmon polaritons. They have been extensively studied, mainly in the visible range, for several decades. And there are actually already some applications available and many ongoing research related, for example, to nanoparticles, which Marek is doing. And IHSOL, for example, I think IHSOL has a project where they want to introduce nanoparticles into brain and try to code some information or to decode it. But one of the most important applications commercially available is surface Plasmon sensor. When you have a metal surface with a prism, you excite plasma, then you see resonance feature like a minimum in reflection. And this feature moves depending upon the dielectric permittivity of a sensed material. And actually all this community, or all this activity in surface Plasmon was boosted in late 90s by Thomas Edison when he discovered the extraordinary transmissions through array of small holes made in metal films. And when you make such an array of holes, you could efficiently couple to surface plasmons in metal films. And by controlling the distance between these holes, you could control the light which passes through this array, and you could even make some color filtering based on such arrays. But these plasmons work, these concepts work well in the visible range, where the dielectric permittivity, as I mentioned, would be negative. But if we go to other frequencies, because the electromagnetic spectrum is very wide, for example, we have terahertz frequencies for security, we have mid-infrared frequencies for sensing, then in some frequency regions, these plasmons simply do not, well, they exist, but they don't work for us, they are useless. And a very important region is mid-infrared, because at mid-infrared frequencies, light interacts strongly with organic materials, with materials which contain carbon atoms, because the carbon atoms have vibrations at mid-infrared frequencies. This is why this frequency range is very relevant. But this is exactly the range where you don't have plasmons, because the dielectric permittivity of metal is so big and negative that it is nearly infinite. So the light which falls onto a metal surface gets reflected 100%, and it cannot be trapped by the surface. So people suggested some solutions of this issue, and they started to structure a metallic surface. So they created, for example, domino-like. In other words, like you introduce air regions into metal, and then effectively you reduce the value of your dielectric permittivity. It's not infinite anymore, but it is still large, and it could support surface mode. So such surfaces could trap electromagnetic waves. But if we plot the dispersion of these waves, where the dispersion is basically a function of frequency is a function of wave vector, and then you plot the dispersion of light traveling in free space, both dispersions really look very similar, which means that these plasmons are nearly indistinguishable from the light that propagates in free space. So for us, they are not very relevant. We want really to manipulate light on the nanoscale, and in this case, mid-infrared light, which has a wavelength of 10 microns, more or less, or more. And then there is another kind of polaritons, which are called Phonon polaritons, because some materials, some polar materials could have lattice vibrations. And when atomic lattice vibrates, then it also creates an excess of charges, and then it induces dipoles, and these dipoles could propagate together with electromagnetic field. So these objects are called Phonon polaritons. And close to transfer optical phonons, and between before reaching longitudinal optical phonons, there is a range of dielectric permittivity which is negative. And as I explained to you before, in this frequency range, we could have surface waves. So we could have surface Phonon polaritons. And these waves have been known in polar bulk crystals, such as, for example, silicon carbide, silicon oxide. And in principle, you could manipulate light using such crystals. However, for example, silicon carbide is very challenging in fabricating, in nano engineering. If you want to make some structures, this is really, especially in thin slabs, this is very difficult. And silicon carbide has an issue of large absorption. So your waves, which you could excite and manipulate, they decay very quickly. And this material are also not very interesting. But recently, a bunch of new materials has appeared, and this was kind of a revolution in nano engineering. This is a concept of so-called van der Waals materials. These are materials which consist of individual atomic layers, which are stuck into multi-layer, and these atomic layers are retained by electromagnetic interaction, which is called van der Waals forces. And the good thing that you could exfoliate such materials, so you could detach one layer, second layer, third layer, and make engineering not only on nanoscale but also on the atomic scale level. Here I want to show you an example how you could exfoliate. This is from an old video from nanoGUNE. How you typically exfoliate thin slabs of such van der Waals crystals. So you could use a Scotch tape. You place a bulk crystal onto, well, there is a special Scotch tape which is very strong. You place a piece of a material which could be graphite, and then you could make graphene or multi-layer graphene. And you do like this, you exfoliate first. It looks to be simple, but you have to have patience for it, because you need to repeat it many, many times. So then you repeat it again and again and again. And then you have many flakes of different thickness. And then in order to know what is the thickness of the flake, you could use two approaches. First, you could use optical microscopy. You just go to the optical microscope and you see your film. And then, because there is interference phenomenon in thin films, each film of each thickness would produce a different color. And then typically in such labs, you have a color scale for each material. And then by color, you could more or less recognize what is roughly what is the thickness. So this is exactly what I say. You see, there could be flakes of different colors. And then according to the table, you know more or less what is the thickness. But then, in order to be more precise, you go to amplitude force microscopy and you measure it with not even nanoscale, but with Armstrong resolution. And yeah, this is how they exfoliated. And the good thing about these materials that many of them support polaritons, and not only Plasmon polaritons that I mentioned in metals, not only Phonon polaritons, but also they could be exciton polaritons, even Cooper pairs polaritons, which are very exotic objects, Magnum polaritons. So in general, polaritons could be defined as quasi-particle or physical objects, which has both parts. One is electromagnetic field, and the second one are in dipoles induced in a crystal or in a medium, and they are coupled. So you could see it as a wave, which involves the oscillations of induced dipoles. And these induced dipoles could be because of lattice vibrations, and because of freak atoms, and because of many other things. But today I will focus on phonon polaritons. So now we're at the point where I have to explain what I mean with hyperbolic. In general, when we talk about dispersion, we usually plot, well, at least in optics, frequency is a function of the wave vector, which is an inverse wavelength of the light. But in general, the dispersion is a relation between frequency and momentum, which is a vector, the same as in condensed matter. We have momentum energy. And we have three components of momentum and the energy. So we have, in principle, our dispersion present a surface in a four-dimensional space, which is impossible to imagine. This is why typically what we do is fix in one of the variables, and then we can represent in 3 dimensions. So here we could fix the frequency, and then we have a so-called isofrequency surface in 3 dimensions, which could be really complicated, and especially taking into account that the momentum could be complex. So each component of the momentum is a complex number. Then you should multiply your dimension space by 2. Instead of 4 variables, you have 8 variables. So in principle, the dispersion is a surface in 8-dimensional space. But typically, we forget for the moment about absorption. So we have 3 components of momentum and a fixed energy. And then in case of free space waves, we end up simply with a sphere, because this is a dispersion of light in vacuum, and it is a sphere. And actually, all the wave vectors which are inside the sphere, they correspond to plane waves, which could transmit energy. So these are propagating waves. But all the waves which are outside of the sphere, they are evanescent waves. These waves decay exponentially in space, in one or the other way. And actually, as you could see, the most of the waves are evanescent, because the evanescent wave occupies the whole space. And now, if we think in a material which presents a layer structure, which are called, for example, this could be uniaxial crystal, which is shown, but there could be also biaxial. Well, when you have an anisotropy in plane, and this is what I will focus on later. Then, if you plot the dispersion, it's not sphere anymore, but in some cases, for example, when one of the components of the tensor, because for such crystal, you have to introduce the electric permittivity tensor. So if one of the diagonal elements is negative and the other one is positive, then you could have a fancy shape for your isofrequency curve, which could be hyperboloid. And it could be either closed or open. Then you could classify in between type 1 hyperbolic waves or type 2. And the good thing about such dispersion surfaces is that, oppositely to the isotropic case or the case of free space, here all the wave vectors which are outside of the hyperboloids correspond to propagating waves, but the ones which are inside are evanescent. So now we have an access in this material to a huge range of propagating waves, and thus we could, for really high momentum, we could reach small wavelengths, and thus we can manipulate light on very, very small scales. And such crystals were identified, for example, in 2014, right? There was identified hexagonal boron nitride, and such a material has several optical phonons, and these phonons are shifted in frequencies. And if we here plot the electric permittivity function, the electric permittivity tensor, both of the elements, transversal and Z component, longitudinal, as a function of frequency, you would see that there are 2 strong phonons, and these phonons are separated. But then there is a range where one of the components of the electric permittivity tensor is negative, and the other one is positive, and here is the opposite. And then in these narrow bands, we could have hyperbolic dispersion. So it's a natural material, and this is why this is very interesting, because before such kind of wave propagation was studied in artificial media. Now we have access to natural crystals. And a very remarkable feature of the hyperbolic waves is that when you use a point source, imagine if we place a point source on the surface of boron nitride, and then in the air, first you would see evanescent fields quickly decaying from the dipole. And if you go far away, you would see propagating spherical waves. But in the crystal, you see something like rays, which we call hyperbolic rays. These are not rays which you know from ray optics. We just call them rays because visually they behave like rays. And actually, these rays originate from the asymptote of your hyperbolic dispersion. So if you plot as a cross-section of your isofrequency surface, you would get isofrequency curve at fixed momentum in right direction. And then hyperbola has asymptotes. And then this straight line correspond to these asymptotes. Why? Because the density of states here increases with the wave vector. And then the larger the wave vector, the more waves tend to stay here. And this is why you see wave vectors with large K, you see waves with large K vectors, and you see these rays. And amazingly, now if you make another surface, so if you have a slab instead of bulk crystal, then this ray could just reflect, and you see a zigzag type pattern. And actually, to impress you, this is the half of the wavelength of the infrared light, and this is a zigzag pattern. So you see this, that this pattern is much smaller, has the dimensions much smaller than the wavelength, which is amazing. So we could create fancy patterns at the scale which is deeply sub-wavelength. And also interestingly, that these field patterns we can represent in terms of waveguiding modes. For example, like in quantum mechanics, we could project an electronic state into some simple wave functions. Here we can project our complex electromagnetic field into waveguiding modes. This we can do mathematically. And if we do it, then we end up with an infinite set of waveguiding modes, which are quantized in the vertical direction. Okay, they propagate here along the slab, but they are quantized here. And with the number of modes, you see more oscillations in the transversal direction. And if you sum up all these modes, you end up with this zigzag pattern. And interestingly, each mode has its own dispersion. In the mathematical, for the math, you have an infinite set of modes, but in reality, the number of modes is equal to number of monolayers in your slab, but it's a huge number, typically for several 100 nanometer thick film. And the more is the quantization number of the mode, the larger is the momentum. Okay, in principle, and since this wave decays, zigzag cannot exist in spaces in the scale much at a very big distances from the source because they decay quickly. So you see the zigzag only in the vicinity of the die. And also, I would need to highlight here that these waves are really deeply subwavelength. So the wavelength is small, and then the wave vector is large. Actually, if we here plotted the dispersion of light in free space, this will be just a vertical line. And then there is a strong mismatch in momentum. So in order to couple to these waves and to manipulate, we have to fulfill the energy and momentum conservation. At a fixed frequency, we need this missing momentum. So how we can deal with that? In principle, the momentum conservation occurs because we have translational symmetry. Our crystal is symmetric. So it's the same from minus infinity to infinity along the crystal. This is why the momentum has to be conserved. But then we can introduce a defect, and then the defect breaks the condition of momentum conservation. This is how you could excite and access your waves. You just introduce a defect. But our idea was not only to do that, not only to match the momentum, but also to somehow enhance this process. And you could do it by just looking into engineering, into radio wave engineering, where people for already a century have been transforming light into electromagnetic, into the current. Okay, so this is the concept. You have a radio wave antenna. It's a piece of wire where you could see it as a Fabry-Perot interference, because this wire supports plasmons, which are not confined, but still they are in this wire, and they propagate back and forth, and they create Fabry-Perot resonance. And then you could enhance radio waves, and you could transmit them into current. So we thought in the same concept, but to convert light not in the current, we also did it. Not into the current, but into the polaritons. So for that, we also take a metal rod, but much smaller. This is more or less, to give you an idea, the smallest of the mid-infrared antenna. This is a human hair. So you take this antenna, these are nice experiments from Rainer. And then you illuminate it with light, and you have plasmons in this small rod. They propagate back and forth, and they create Fabry-Perot resonance, and this is how dipolar antenna works. And then this antenna allows you to overcome the momentum mismatch. It could also lodge polaritons. This is what we checked, and it nicely worked for the case of boron nitride, for example. And we also did it experimentally, and this works really, really nicely. So the efficiency is very good here. Also, we tried to couple with polaritons using photonic crystals. You know that photonic crystals are structures, nanostructures, periodic nanostructures, where light could exist in the form of block states. And then because of break diffraction, you could directly couple to the block waves by illuminating. And these photonic crystals are now widely used for the enhancing light emitting diodes, efficiency also in fiber communications and even in the surgery. So we repeated this concept for boron nitride. We just drilled hole there in a very small holes, and then we managed to create a photonic crystal, the size of which was so small that if this photonic crystal would be realized in a normal dielectric, it would correspond to just one unit cell. So imagine in a dielectric slab we have holes in a normal photonic crystal, but then in such materials, the whole size of photonic crystals reduces more than 10 times. So we can repeat all those concepts developed for normal photonic crystals, but now in these van der Waals materials. Another kind of excitations could be cavities. Normal optical cavity has two mirrors, where in between of these mirrors you have reflection of lights, and then you create the resonant condition. So we could do the same, but instead of mirrors, we just take an antenna made of boron nitride. And then we have, as you remember, you could have waveguiding modes here, and then just reflect back and forth. And then you could create dipolar antennas. And then we demonstrated experimentally that you could really generate hotspots with such small antennas. You see, this is 10 microns, so this is one wavelength. And you have many antennas here. Why this is relevant at all, and which applications could be thought here? So one of the applications, this is what also I'm partially involved into the activities at Ryder, is developing nanoGUNE. So these are photodetectors, room temperature photodetectors for terahertz, and because some of these materials supports polariton in terahertz frequency range, but also in mid-infrared. So how could you make use of these hyperbolic waves? Imagine that you have a graphene monolayer, and this graphene, as you know, the Fermi level could be manipulated simply by placing a gate, a metal pad, and applying voltage. If you have graphene on top separated, you have a field effect, and then you could induce charges into graphene. And then imagine if we split this metal pad into two parts and apply two different voltages. Actually, you could apply one positive, another negative. And then in graphene, you create artificial pin junction. In the vicinity of the pin junction, you have a quick variation of the electron of the charge carrier density. And now, if you heat up this region somehow, and you have a gradient of temperature, then multiplying gradient of temperature with the gradient of charge carriers, you have the current. And this is how photodetector works. So here, this is a split gate electrons, which also works as an antenna. So we enhance radiation here in this gap, but we apply positive and negative voltages. We create pin junction. And then the current flows through these electrodes. And importantly, now the graphene, which shows the best mobility, is inserted into boron nitride, because boron nitride protects graphene a lot, because the boron nitride lattice somehow matches very well with graphene lattice. And then this is graphene which shows less impurities and the highest mobility. And this is exactly where we have hyperbolic waves. Now, if we place a slab of graphene, monolayer graphene in between of two boron nitride layers, we could generate these hyperbolic waves. And here, for example, where this hyperbolic ray reflects, you create a strong hot spot. And in this hot spot, you have, as I mentioned, gradient of temperature, and then you could substantially enhance the efficiency of your photodetector. So this is one of the direct applications of hyperbolic waves, hyperbolic polaritons. And now I would like to mention that all these hyperbolic phenomena that I mentioned for boron nitride, they take place inside of the crystal. So there are rays which propagates inside the crystal perpendicular to the face. But if we want to see these rays somehow in a microscope, we need them to be realized in plane along the slab. And this is what you cannot do with uniaxial crystal, but you can do it with biaxial crystal. And actually, a few years ago, we identified a biaxial vanillus crystal, which is alpha molybdenum oxide, which has a fancy crystal lattice. And most importantly, it has many vibrations at mid-infrared, which are spectrally well separated. And then we used, in Rainer's group, we used nano imaging with scattering field, near field microscopy, which uses a thin tip with a nanoscale tip apex radius, and then you could focus the radiation at the end of this apex. So here I could show a video from NASPECT, a piece of it, so that you see what the microscope looks like. So it is based on AFM setup. Actually, this microscope was developed by Rainer. So Rainer is, I would say, the pioneer of all this microscopy, and also the developer of this microscope. So you have a tip, and then this tip is illuminated by external beam. It focuses radiation here, and then you have scattered light, which is captured by the detector. And then you move your sample below the tip, and you record the signal as a function of sample position. And then you create a near field map of your sample. And the resolution in this case is only limited by the resolution, by the curvature radius of your tip. This is how this imaging works. So we used this concept, but applying to polaritons, and we call it polariton interferometry. How it works? So we have this tip, and we illuminate light. It acts actually as an optical antenna, but now it is vertical. It has a field with large components of K vectors, and they launch polariton as a cylindrical wave. Okay, then this polariton propagates toward a defect or toward the edge in this case, and this edge reflects back also the cylindrical wave, and they interfere. They interfere, and then this interference field is scattered back to the detector, and you record the signal as a function of the position. Actually, this is how some animals also recognize objects, like a hunting bat. And then to show you the near field image, this is an example of exactly boron nitride. Since it is isotropic in plane, you always have polaritons launched in any direction, but they are reflected back from this edge and from this edge, and this is why you just see the stripes, which are nothing else but interference stripes. You see interference. But some other colleagues from China, they identified this MO3 crystal, and they applied such a polariton interferometry, and they saw that in one of the directions there are no fringes, which was really puzzling. And then they asked for the help, and we helped them. Well, we repeated it also in nanoGUNE, and we helped them to interpret these results. Actually, it turns to be that such material has hyperbolic dispersion in plane. So you have these isofrequency hyperbolic curves in plane, which means that the launch polaritons has hyperbolic wave shape, and there are some directions where polaritons cannot propagate. So they cannot propagate here, and thus you don't see any reflection. You could just see reflection here along one of the axes. And then in order to prove that we indeed have hyperbolic waves, we just cut out some circles. So we cut out disks out of MO3 slab, and then we just imaged the disks, and then without thinking too much, we Fourier transformed. So from real space, we went to a K space immediately, and then you see clearly, in one case you have ellipse, and another one you have hyperbola. So actually we realize that there are several bands where polariton polaritons are anisotropic, but they could be either hyperbolic or elliptical. And then we actually, with help of Ion, we extracted the electric function, because when we were doing this experiment, we had any idea of how the dielectric permittivity was in this material and how to model it. And then Ion helped us to extract the dielectric function using density function theory simulations. And then we also made some additional experiments in the United States. And now we have this dielectric function, and we can model all these wave phenomena, these crystals. And most importantly, we realized that we found a natural platform for testing hyperbolic nano-optics concepts. So you could have either hyperbolic wave phenomena or normal wave phenomena, or like elliptical shape of your wavefronts. And one of the examples of how this hyperbolic nano-optics works was to demonstrate it through refraction, hyperbolic waves. So refraction, as we know, is just bending of light when it enters into a medium. Like in a glass with water, we see this spoon would look like this. And this happens because we have the momentum conservation along the surface. The momentum, the in-plane momentum is constant, and the out-of-plane momentum is already adapted to the dielectric permittivity, to the medium. It could be larger. Okay, and this is why you have bending of your light beam. Also, you could see it here in the isofrequency plots. This is just the cross-section of a sphere in vacuum, and this is in the dielectric. And very important that for waves in normal media, let's say normal in conventional media, the Poynting vector, which is green, is parallel to the k vector. And this is why the energy flows in the same direction where the phase. But now, if we have one with a medium is hyperbolic, this is not the case, because the Poynting vector and the k vector are non-collinear. So the energy flows in one direction, but the phase propagates in a different direction. And this complicates thinking about that. Actually, this is how people have illustrated how it would look like if such media exceeded at visible frequencies. So we still have the conservation of the in-plane momentum, okay, for the red arrows, but the green arrows would be like this, for example, because actually the Poynting vector is perpendicular to the isofrequency curve, and in case of hyperbola, especially close to asymptote, it becomes completely perpendicular. So the energy flows in the direction which is perpendicular to where you see the wavefronts. So this is very exotic, and this is why you could have such phenomena as, for example, negative refraction, as illustrated here. So the energy flow in the same direction from where it comes. And then if we have two hyperbolic medium, then actually you have whatever situation, because you could have any orientation of Poynting vector with respect to k vector, and you could end up with negative, positive diffraction. So this is much more, it's a much richer platform than conventional medium. So you see, depending upon the hyperbola, the refraction could be arbitrary. And then to illustrate how hyperbolic waves refract, we tried to make an experiment where we needed two different hyperbolic media. But how can you make two different media out of the same crystal? Well, the idea was to place the crystal on top of a substrate, actually, and on top of another substrate, or just surrounded by air. Because, for example, the dispersion of the fundamental zero mode, as we call it, in a slab, which is in the air, is like this, is a blue curve, but the one which is placed into silicon oxide is here. So you see that the dispersion is different. And if you draw the isofrequency curves, they also will be different a little bit. And then you have already two different hyperbolic media. You could do it by just introducing a hole into silicon oxide substrate, and then the dispersion of waves here would be different than the wave here. Then you could have two different hyperbolic media. And then You could also, well, this is quite complicated, but to explain it quickly, you could have different frequency curves. Then you have to take into account that the momentum is conserved along, if this is the boundary between two medium, the momentum is conserved, and then you see how the Poynting vector is directed. And it could be directed differently depending upon the frequency. And then we realized it experimentally. Okay, so we just used the same microscope as s-SNOM, but instead of using metal tip, we use the electric tip. So the tip in this case does not excite anything, just scatters the field, and then the signal is proportional to the field which exists in our structure. And then we excite the fields by plane wave. We place an antenna here, and this antenna launches, let's say, plane or close to plane wave waveforms, and they pass through this prism. And this prism is just a hole in the substrate. And you nicely could see how it refracts. And actually, the Poynting vector is directed here. Well, the K vector is directed here. And this is the simulation. This is the experiment. Because we have this nicely extracted dielectric function, we reproduce perfectly now all our experiments. And then an interesting thing here is that we paid attention that this wave, it gets bended. And we thought maybe we place another prism here and we could have focusing. And indeed, we make, well, this is at a different wavelength. We make such a shape, prism like or triangle-like shape. And then both in the simulation and the experiment, we observe the focusing. And then if the slab would be isotropic, we would observe something like that. So nothing interesting. But in case when two media are hyperbolic, you could have a very narrow focus. So you could focus light in really small dimensions. And then the same concept we used for metallic antennas, because we always could use Huygens principle. So if we place many point dipoles on the surface, they would emit a radiation pattern like for this surface. And then we tried with point dipoles to mimic also some focusing phenomena. And then we repeated this surface, just cutting out a metal disc out of metal slab and then placing it onto the MO3 crystal. And then we nicely saw this focusing. And this what would happen for isotropic crystals. So the you would need to make an inverse curvature. So if we lived in a hyperbolic world, instead of parabolic antennas, we would need to have such kind of antennas with an inverse shape. So am I out of time? Then I just very quickly introduce you into, well, these are just experiments and simulations of different wavelengths. We could see that changing the wavelength, we could change the position of the focus and the size of the focus, so we could nicely control hyperbolic waves. And just to briefly introduce you into field of twisted nano-optics. So you might know this experiment. Actually, Paco Guinea is actively working on twisted graphene bilayers, because some years ago there was superconductivity that detected and twisted bilayers when there is a so-called magic angle. When they're twisted at a very small magic angle, you create a Maury superlattice, and you have long-range correlation between electrons, and you could reach superconductivity. But also such superlattice, Maury superlattice, has periods of light in the visible range, and also it could have periods of polaritons, which live in graphene. And this is why, for example, by group of Dmitry Basov, they introduce a concept of twisted photonic crystals. So they use this Maury pattern to manipulate plasmons in graphene. But we wanted to test this concept just by rotating slabs of MO3 relatively to each other. And then we realized that when you rotate the slabs, and if you plot isofrequency curves of polaritons living in these slabs, the evolution is like that. So they go from open isofrequency curve to closed, and there is a topological transition here. So when open surfaces become closed. And very interesting is that close to this topological transition, the isofrequency curve becomes flat. And then all the wave vectors coming from the center of this Fourier space correspond to the same direction of the pointing vector. And if you now take a point source and image the fields emanating from the point source, you see that here you have hyperbolic waveforms that I showed you before. But here suddenly you have all the waves traveling in the same direction. So we call this the so-called canalization regime, when you can canalize, when you create natural waveguide, you don't need any boundaries, you don't need to cut anything. You just rotate two slabs and you have a nice waveguide. And now we work with 3 layers. We have demonstrated that such waveguidance is very stable. It exists in a large frequency range. So very interesting stuff. And then we repeated it experimentally. So for different twisting angles, we twisted the same flakes at different angles, and then by using the same concept, placing an antenna and mapping the fields with the silicon tip, we saw that at a frequency which more or less corresponds to topological transition of the isofrequency curves, we achieve this canalization. You see in the microscopic image, you have this light canalized, and this is just a hyperbolic waveforms. And then we call this twisted nano-optic, which Nathaniel has been doing this method. Okay, then I skip all these interactions with molecules. This will be for the next time. Unfortunately, the video will... So, and I will give you take-home messages that we have seen that van der Waals crystals support a big family of polaritons, and amazingly, these crystals could be either uniaxial or biaxial, so we could have anisotropic wave phenomena in plane, which could be observable in state-of-the-art microscopic tools. Then we observed and simulated the refraction and reflection and characterized the propagation of such waves along these crystals. And then we studied how these waves behave in twisted slabs configurations and found that there is a regime which we call canalization. So you could create natural waveguides along certain directions. And of course, I would like to acknowledge our friends and collaborators from Quantum Nanophysics Group. Now Pablo Alonso here, he has got the second ERC. So we're very happy about that. And also, of course, to Ryan's group, which we also are friends and close collaborators. He has contributed a lot to this field. And also to some other teams and to some financial support. And thank you very much.
Thank you very much, Alexey. We have time for questions. So please.
How thick are the MO3 slats that you are twisting? Or
I think in that case was like something between 80 and 100 nanometers, both of them.
okay, so you can consider it as 2 bulks, right? Somehow it's
well, maybe for phonons, yes, but for phonon polaritons, it's very crucial that they have a finer thickness because the field is quantized. So the field is trapped in between the band. This is why actually the thinner the slab, the shorter is the wavelength that is supported by this. So the thickness is very crucial.
More question. I mean, if there's no question, it will
Yeah,
crystal clear, you know.
Or the opposite.
No, it's clear. I have actually one question regarding this photodetector. So which wavelength you can detect with this?
Well, in principle, this photodetector operate. Well, not operate because we are still trying to design. They're supposed to operate from infrared to terahertz, covering all this range, and at room temperature, which is the main advantage.
But in this design, can you somehow design the system for the specific wave or range?
In principle, you could design it for all frequencies on the same. Well, the efficiency would be very different, but I think if you design it smartly, it would be valid for all wavelengths, for all the spectrum.
when you compare the experiment to the theory, it seems that the position of the maximum and the intensity of the maxima is the same, but for the minima, what you get in the experiment is color is very different from the theory. What is the reason for that? Or it's just because
in which, sorry, excuse me.
if you take any picture where you compare theory and experiment.
I don't remember where I had it. In the simulations, maybe right here.
Yes, exactly. So the maxima in red seems to be the same, but then in the experiment you have these blue regions. While in the theory you get to just gray.
Yeah, the point that we compare like these images, but actually they are very different because here we just represent the electric field, but in s-SNOM you measure something, a signal, which Rainer calls near field signal, which somehow we think that it could be proportional to this field, but it is not, because you have the ground, also the tip is oscillating, and then you have to demodulate and Fourier transform. So you apply a very complex operation to your data, and then you see that okay, your data is very similar to the field, and then we believe that we map the field. But this is not the case, and because of the interference, you shift everything, because your interference shifts the position of minima and maximum, and also spectrum. Thomas.
I have a very naive question about hyperbolic line. Can we think of group velocity for these?
Yes, and it's a very interesting question, because the group velocity normally is defined as a derivative. So frequency, the derivative upon the wave vector. And with this, we should be very careful, because all this dispersion could look like that your derivative becomes zero, for example, or it becomes negative, or even infinite. So there are many situations here available, and sometimes we even need to redefine the group velocity, because this definition is not valid anymore. But sometimes we observed here, for example, a region of negative group velocity, when the derivative becomes negative. But it doesn't mean that the energy flows in the opposite direction, because the energy is given by the Poynting vector flux. So it's a very tricky business with this group velocity, which people speculate a lot actually.
Good. If there is no more questions, so let's thank again our speaker. Before you leave, so there is a small surprise for you. Basically, you have a food. I know this is the lunchtime, so just before starting in the lunch, so we can go to the room and then basically have some refreshment over there. Thank you very much.
What can I learn more about this channel?
And I put in there. So I mean, basically the back ecosystem